Welcome back. In the last session we solved problem number 14, right? And that is nothing but your low pass filter, but second order low pass filter, and the problem is simply related to qualitative analysis, asking for type of filter, and then we solved it. And then later on, just to complete the theory, we solved the transfer function and we got to know that there are two poles, right? Then finally that is nothing but having a DC gain which is R2 by R1 magnitude and having two poles, therefore it is low pass filter. Okay. Now problem number 15. Problem number 15. Given the ideal op amp circuit shown in figure, indicate the correct transfer characteristics assuming ideal diodes with zero cut-in voltage. Okay, we didn't solve this type of problems. Okay, this is the first time we are solving. Then you can take it. Problem number 15. Circuit is given minus, plus, this is VI, okay, and it is given with plus 10 volts and minus 10 volts, and asking for correct transfer characteristics. I'll give you two options, then you can continue for the same for other options. And then given like this is VI and this is V0, saying that this is minus 8 volt and this is minus 5 volt. Okay, and this is plus 10 and this is minus 10. Okay, then option B, plus 10 minus 10, this is VI, this is V0, and this is 8 volt and this is minus 5 volt. Okay, this is what is given in option C, option D. Okay, what it may be, and you have options also. Okay. Listen, don't write anything. How to solve the problems? These type of problems. Okay. Now, and then after solving the problem, I'll explain the significance of the problem and what is this problem and what is this circuit. Okay. Even though this is a problem, but it is covering the theory also. That is what I'm explaining now. Tell me, is it a negative feedback or positive feedback or open loop? That depends on diodes, right? We don't know, right? Let us say this is what is diode D1 and diode D2. This is diode D1 and diode D2. Definitely one of the diodes will be conducting, no doubt about it. Right? Why? Let us say both are not conducting. If both are not conducting, then open loop, then comparator, then your output voltage will be either plus 10 or minus 10. If output is either plus 10 or minus 10, definitely one of the diodes will be conducting, no doubt about it. If one of the diodes is conducting, then let us say D1 is conducting, then there is a positive feedback. Remember, this is not having negative feedback. Now op amp is configured in positive feedback. If op amp is configured in positive feedback, virtual ground concept is not valid. Then what is this? This is nothing but a comparator. That is what I told you, right? If op amp is configured in positive feedback, we should not use virtual ground concept. We have to use or we have to treat the problem like a comparator. If problem is comparator, it depends on the value between minus to plus, right? If minus is more than plus, output will be minus 10. If plus is more than minus, your output will be plus 10. That is what I told. That is nothing but a comparator. Now, what are maybe I can say how to start the problem, how to solve the problem. Simple. Once you know that this is in positive feedback or open loop, simply take your output voltage one of the power supplies, because you'll get one of the power supplies as your output. Either you can start with plus 10 or you can start with minus 10. That is what is starting point of the problem. Everybody understood? If op amp is in positive feedback, it is a comparator. If it is a comparator, your output voltage will be either plus VCC or minus VCC. Then start with either plus 10 or minus 10. Then solve the problem. You'll get the answer. Got it? Let me start. Anything is fine. Therefore, then based on the output, I am going to tell the state of the diodes. Let us say case 1. When V0 is equal to plus 10, let us say, then tell me the states of the diode. This is positive feedback problem. Therefore, this is positive feedback problem. Virtual ground concept is not valid. Virtual ground concept is not valid. Okay, that's fine. Now, when V0 is equal plus 10, then what is the state of the circuit which is on? When V0 is equal plus 10, can I say your D2 is on and then D1 is off, because this is plus 10. Then D2 is on, D1 is off. Therefore, D2 is on and D1 is off. Right? Therefore, now tell me, then what is the circuit? Don't disturb original circuit. You have to draw once again. Okay? Minus, plus, this is your VI. Now, D2 is on. When D2 is on, D1 is off means it is floating. Don't represent that. Okay? This is nothing but 2 kilo ohm and this is 0.5 kilo ohm. Now what is your output? Your output is plus 10 volts. Right? Your output is plus 10 volts. Then this is what people call it as beta network. Means this is in positive feedback. Open loop amplifier and then beta network. Then what are output voltage we have? Sampling the output voltage and feeding at the plus terminal. What it may be? Let me call how much we are sampling or how much we are feeding back. Right? That is nothing but your beta V0. That is what people call it as beta V0. Therefore, what is beta V0? This is another beta network. Right? Therefore, what is beta V0? Beta V0 is equal to, beta is nothing but 2K. This voltage divider network. 2K divided by 2K plus 2.5K. 2K plus 0.5K. 2.5K into V0. V0 is nothing but 10. Then tell me what is this? KK will be cancelled. 2.5 into 4, 8. Therefore, this is 8 volt. Therefore, what is beta into V0? That is 8 volt. Therefore, what is voltage? When V0 is equal to plus 10, then it is voltage divider network because current entering into op amp is 0. It is like floating. Input impedance is infinity, it is floating. Then it is simply 2K divided by 2K plus 0.5K then into V0. That is what is the voltage we have here. Then this is what is 8 volt. Therefore now tell me, if I plot the curve, input is Vi, output is V0. What is threshold voltage or break voltage? 8 volt. Therefore let us say this is what is our 8 volt. Therefore now tell me, you are sweeping your input voltage from minus infinity to plus infinity because it is a comparator. It is comparing between plus to minus. No virtual ground concept, no nodal analysis. Remember, okay? We can do nodal analysis. It's not that we cannot do nodal analysis, but nodal analysis is to find the voltages. But now already we know the voltage 8 volt, but don't say this is 8. No. That is what is driven by Vi. This is what is driven by V0. There is no tracking. The tracking is there. Our virtual ground concept is valid only when the op amp is in negative feedback. Okay, that is fine. Now this is 8 volt. Now tell me, this is what your Vi. When I say this is what your input voltage, right? When input is swept from minus infinity to plus infinity, therefore Vi is swept from minus infinity to plus infinity. Then tell me, let us say minus 100. When this is what is minus 100, let us say this is minus 100. And this is 8, which is more? This is minus 100, this is 8, which is more? 8 is more, then plus is more, output will be plus 10. Fine, because it is a comparator. Now, minus 100, but this is 8, okay? Your plus is 8, but minus value, minus 100, minus 50, minus 10, 0, 1, 2, 3, 4, 5, 6, 7, 8. Once the minus value or input value is crossing 8 volt, then it is crossing plus non-inverting terminal voltage, then your minus will be more than plus, then your output voltage will switch from plus 10 to minus 10. Therefore, your output will be switching from plus 10 to minus 10. It will switch from plus 10 to minus 10. This is what is the direction of the arrow, saying that when input is swept from minus infinity to plus infinity, your output will switch from plus 10 to minus 10 with a switching point of 8 volt. Therefore, what is the switching point? Our threshold voltage, our comparison voltage, that is what is 8. When output is 10, this is 8. When input is crossing 8, then output will be switching from plus 10 to minus 10. That is simple, right? But once input crosses 8, then if you come back, then now the switching point is not 8, it will not become minus 10 to plus 10. No, now the switching point is different. When output is switching from plus 10 to minus 10, now this is what your original circuit. Now when output is minus 10, now D1 will be on, D2 will be off. Now the state is changing. That is what is the circuit. Now let's see what is that. Now case 2. Now V0 is equal to minus 10 volt. When V0 is equal to minus 10 volt, tell me, this is original circuit, not this. This is derived from the circuit assuming V0 is 10. When V0 is 10, this is the circuit. But now, from this only we got to know that there is a switching from plus 10 to minus 10. When output is becoming minus 10, don't use this circuit. We have to go to this original circuit. When output is minus 10, which is conducting D2, minus 10. This is off, minus 10. N is connected to negative. Therefore, D1 will be on. Your D1 will be on. D2 is off. Then tell me what is your circuit. This is again derived circuit based on your output state. Now this is your Vi. You have to solve all positive feedback problems like this only. This is the blind procedure for positive feedback problems. Now tell me what is V0. V0 is equal to minus 10. Okay. This is 2 kilo ohm. This is also 2 kilo ohm. Because diodes are ideal, when diode is on, short circuit. When diode is off, open circuit. Okay. Now, let's see. When output is minus 10, again let's find beta V0. It is straightforward. Both are same, right? Half volt is here, half volt is here. Therefore, now this is minus 5 volt. Therefore, what is the voltage at plus minus 5? Now, if I plot the curve, this is what is your Vi and this is what your V0. Therefore, tell me what is the switching point here? The switching point is nothing but minus 5. Just a minute. Now the switching point is -5. Therefore, now tell me, when you sweep your input from plus infinity to minus infinity, already minus infinity to plus infinity is already covered. Now when input is switching from plus infinity to minus infinity, reverse direction, then tell me, let us say input is 10 volts. Input is 10 volts. Then 10 and then -5. Which is more? 10 is more. Minus is more. Output is -10. Satisfied? Let us say input is 5. 5 and then -5. Which is more? Minus is more. -10. Input is 2 volts. Which is more? 2 is more. Minus is more. -10. Input is 0. Which is more? 0 and then -5. 0 is more. Minus is more. -10. Input is -1, -2, -3, -4, -5, -6. Let us say -6 and then -5. Which is more? Plus is more. Now it will become +10. Therefore, when you come from plus infinity to minus infinity, that -10 will become +10. It will become -10 will become +10. But what is the switching point? The switching point is -5 volt. Therefore, if you ask me the direction, this is what is the direction. When input is switching or when input is sweeping, swept from plus infinity to minus infinity, now the switching point is -5. But when input is swept from minus infinity to plus infinity, the switching point is 8. If you combine these two, you will get hysteresis. Therefore, when I combine those two, let's see, this is your Vi and this is what is V0, then it is defined with what? 8 volt, and this is defined with -5 volt. Then tell me, in the positive direction, this is what it is, and in the negative direction, this is what it is, right? Therefore, this is the direction. Now this is the direction. Therefore, this is what is +10 and this is -10. This is what is having hysteresis in between. This is what is called hysteresis. Means it is not having unique switching point with respect to the direction of your input. When input is changing in positive direction, switching point is 8. When input is changing in the negative direction, the switching point is -5. Therefore, hysteresis voltage is 8 minus of -5, 13 volt. 13 volt is your hysteresis. And this is what is called upper triggering point. Your upper voltage is triggered to lower voltage because of input when input crosses 8 volt. Therefore, that is the trigger point. Similarly, the lower triggering point -5. Your -10 volt is becoming +10. Therefore, it is triggered from minus to plus. Therefore, this is what is our lower triggering point. This is what is called LTP. This is LTP, lower triggering point, and this is upper triggering point. Your upper voltage is triggered here, lower voltage is triggered here. Therefore, in between UTP to LTP, that is what is called hysteresis voltage, which is UTP minus LTP, which is basically 13 volts. Therefore, this is what is our hysteresis voltage VH. That is what it is. Okay, and this is what is called hysteresis curve. The hysteresis curve is depending on the direction of your input signal. Okay, but if you take normal comparator, we solved one of the problems, right? In the, I think 2-3 sessions before, right? Sine to square wave converter. That is what I told, right? When apply sine wave, it is converting into square wave. But what is the threshold voltage where sine wave is converted into square wave? 0. In positive direction as well as negative direction, threshold is always 0. There is no hysteresis. Hysteresis voltage is 0. Upper triggering point, lower triggering point is 0 or 0 that time. But here, upper triggering point is different, lower triggering point is different, and it is defined with hysteresis voltage. If switching point is different with respect to the direction of your input signal, that will create hysteresis. Okay? Take it. See, for all positive feedback problems, this is what is the technique, or this is what is the methodology. Simple. Once you know that this is positive feedback problem, just define your output voltage, one of the power supplies. Then derive the derived circuit, then get V0 Vi relation, then next derived circuit, then get V0 to Vi relation, you'll get the answer. Okay? Done. Take it. Maybe if you ask me, I think option B is correct. That is what is option B. Answer is option B. Option C, option D also we have, but I did not plot. I think whatever I plotted, option B is correct. Yeah. This is GATE 2005. This is for 2 marks. Okay. I hope everybody understood the procedure. That is what is very important. If you understand the procedure, you will get the answer for sure. And this is what is called Schmidt trigger circuit. I'll explain. First of all, get the answer. Then let's apply sine wave and then let's see what is your output. Okay. It is also sine wave to square wave converter because it is a comparator. It converts sine to square wave, right? But with the different switching points. That is what is UTP and an LTP. That's why this is called Schmidt trigger. Schmidt trigger will have hysteresis curve. Over. I'll give you 30 more seconds, then we will see. If I apply sine wave, problem is over, but I'm just extending little bit to explain something. And if I apply sine wave, let's see what is the output. Okay. Now just transfer curve is enough to get the output for any input. Okay. Let us say this is what is input given. This is what is the input. Maybe if you want I can take one more cycle, but we can stop with the 2 cycles. Okay, 1 cycle. That is enough. Okay. Now if you see here, is it perfect sine wave? Having increased, right? No, it should not be. Right? Okay. Now let us say I'm applying, this is what is peak voltage of 10 volts and this is minus 10 volts and this is 0. First of all, what is the switching point? We have 2 switching points. One is at 8 volt. One is at 8 volt. This is what is the switching point. And another is at minus 5 volt. Another is at minus 5 volt. Now, tell me. Therefore, when input is increasing, now I want to know what is output. Therefore, what is output? V0. Tell me. When input is increasing from minus infinity to plus infinity, the switching point is 8. Therefore, when input is increasing from minus infinity to plus infinity, forward direction, then switching point is 8. Less than 8, output is 10. Less than 8, output is 10. When input is crossing 8, when input is crossing 8, when input is crossing 8, your output is switching from plus 10 to minus 10. Your output is crossing from plus 10 to minus 10. Right? Now, input is crossed and then went to 10. Right? This should be 10. It's 10. Same only. Okay? Therefore, now, crossed and then went to 10. Again, input is coming back. When input is coming back, now the switching point is not 8. It crossed 8. Now your output became minus 10. When it crossed 8, now input is coming back. Now switching point is not 8. Now the switching point is minus 5. Once the input is less than minus 5, then only your output will become minus 10 to plus 10. Till then it will be minus 10 only. Till then it will be minus 10 only. Therefore, it is crossing. Now, when the input is becoming less than minus 5, when input is becoming, once it crosses minus 10, then again, when input is becoming less than minus 5, then only it will be plus 10. Then only it will be plus 10. Should be flat. Then again, this is what is the switching point. Now the next switching point, again it went to minus 10. Now input is changing from minus 10 to plus 10. When input is changing again minus 10 to plus 10, input is changing from minus 10 to plus 10. Now the switching point is not minus 5, now the switching point is 8. Then it will become plus 10 to minus 10. Then it will become plus 10 to minus 10. Then it is becoming plus 10 to minus 10. Again, this is what is the switching point. It will become, this is what is our, therefore, but the switching point is 8 volt and minus 5 volt. This is what is the switching point. It is not having single switching point. It is having 2 switching points. Therefore, this is what is your UTP, upper triggering point, and this is what is LTP, lower triggering point. In between whatever you have, this is what is hysteresis voltage, which is UTP minus LTP, which is 13 volts here. And this is what is called Schmidt-Trigger circuit. This is what is your Schmidt-Trigger circuit, which has hysteresis curve. Schmidt-Trigger circuit. Wherever you need different switching points, people use this. But practically we don't need hysteresis voltage of 13 volt. That is to have noise margin basically. When input is switching due to any noise, if input is went up and then going down, we should not switch the output voltage. We don't want to see any trigger. We don't want to see any glitch at the output. To do not have that, we can have some hysteresis voltage. When you have hysteresis voltage, even though there is a glitch, when input is crossing, even though there is a glitch is going up and then going down, it will not, because it is defined with some lower triggering point which is different than upper triggering point. then you will not see any glitch. It will be covered. The noise due to glitch will be taken out, filtered because of Schmitt trigger action. Okay, that's fine. People will use like interfaces, analog signal processing to digital conversion. People use Schmitt trigger circuits. Okay, but nowadays the processing is not in analog domain, processing is in digital domain. Therefore, only simply just directly the raw signal will be converted to digital, everything will be processed in digital. But earlier, people used to have the processing in terms of analog, maybe finally just to store or whatever maybe transfer, people used to convert into digital. But now, the processing is also in terms of digital, storage is also in terms of digital, transfer also in terms of digital. Everything became digital. Because of the speed and because of noise margins, because of noise, because in analog we always deal with signal to noise ratio, signal power to noise power. The signal power is decreasing but the noise power won't decrease. But in the case of digital, we can have the resolution, therefore we can detect and correct the codes, etc. Due to like bit error rate or due to the noise, signal to noise ratio, people are slowly and then slowly moving into digital. There are multiple reasons. I'm just saying one of the reasons. But analog signal processing is so powerful. We need minimum number of transistors and low power, low area. But signal to noise ratio was the one which is what is dictating to go for digital signal processing. Along with storage and transfer. We cannot store analog signals, we can store but with huge power. We have analog oscilloscopes, but we need to have power continuously, then it will store the analog signals, but it is power hungry and we cannot transfer analog signals unlike your digital signals, because we don't have detection and correction in case of analog, but in digital we have detection and correction. Therefore, storage and transfer, digital data transfer, right, with error correction and detection and correction, that is what is mainly the advantage of digital, and people went to signal processing, digital signal processing also in digital domain. That's fine. This is what your Schmitt trigger, okay? Now problem number 16. And if you see the square wave duty cycle is nothing but what? On time divided by off time plus on time, or on time divided by total period. Out of total period, then on time is more than half of the period. Therefore, 50%, more than 50% duty cycle. Typically we ignore first half cycle or full cycle, then we can consider next cycle. Okay, that's fine. Now problem number 16. And after that we can go for multi-vibrators. Bistable, astable, monostable. Problem number 16. In the circuit, find V0. Okay. This is GATE 2000 for 1 marks. Problem is what is V naught? Option A minus 1 volt, option B 2 volt, option C 1 volt, option D 15 volt. Okay, now listen, tell me, negative feedback or positive feedback? Positive feedback, not negative feedback. Remember, if you assume that this is in negative feedback and apply virtual ground concept, then if you do nodal analysis, you'll get the answer. That answer will be there in the options. That answer will be there in the options. Therefore, remember, this is positive feedback problem. This is positive feedback problem. When I say positive feedback problem, right, then it is not, virtual ground concept is not valid. I am writing again and again. Next time onwards I will not write. Virtual ground concept is not valid. Right? Then it is nothing but what? Then it is nothing but a comparator. The circuit will act as a comparator. When I say this is comparator, it just compares between these two, voltage at minus and voltage at plus. Then based on that you will get your output voltage. Okay? Now, I told you, right? I told you your output could be anything. When the problem is associated to, when the op amp is associated to positive feedback, your output voltage could be either plus 15 or minus 15. That we don't know. Then you can start with either plus 15. When you start with plus 15 here, let us say when you start with plus 15 here, then we need to find what is the voltage here. Right? When you start with minus 15, then you need to start what is the voltage here. Right? Then based on that you will get it. That we don't know, right? Then we will see. Therefore, let us start with output voltage plus 15. Same procedure. Okay? Now, case 1. Let me start here. Case 1. V0 is plus 15. Actually, no need to solve the problem, strictly speaking. Why? Definitely your output voltage will be either plus 15 or minus 15. Then, if you see the options, right, the options are nothing but having only plus 15. You can choose that. But I need to derive it. I need to prove it. Right? When V0 is plus 15, then tell me what is your circuit? Same circuit, but this is ground. Now, this is what is having resistor, resistor. Now your V0. V0 is equal to plus 15. Then let us say this is what is 1 volt and this is R. Now tell me what is this voltage? That is nothing but a beta V0, or feedback quantity. Right? Therefore let me call this as feedback quantity or voltage at plus. Let me call this as VF. Then tell me VF, how will you get VF? Apply nodal analysis. But don't say this is 0. Okay, I am just trying to find VF. How to find VF? Nodal analysis. VF minus 1 divided by R plus VF minus R, you can apply superposition also, anything is fine. VF minus 15 divided by R is equal to 0. RR will be cancelled. Then what you get? Then you will get 2 into VF is equal to 16. Then what is your VF? VF will be equal to 8 volts. Therefore, what is your VF? VF is equal to 8 volts. VF is equal to 8 volts. Therefore, now tell me, this is 8 volts and this is 0. Which is more? Plus is more. Then 8 volts and then 0 plus is more. Therefore, output is equal to plus 15. Satisfied. Okay? That's fine. Now, let us say output is minus 15. We don't know, right? This is what is satisfied. Now, case 2. Let us say, but tell me, if this is what is the scenario, it satisfies, right? Then if this is what is the scenario, then if output is plus 15, then that's it, done. It will stay there only. It will stay there only, right? Yes, it will stay there only. Answer is 15. But just to complete, if V0 is equal to minus 15, we don't know, right? It could be anything. Let us say I just pulled this V0, or I just applied something, or I applied some trigger such that output became minus 15. I'm just explaining. Problem is over, but I'm explaining the theory. Then what is our circuit? Now you solve. This is minus 15. This is ground. Then therefore V0 is equal to minus 15. Let us say, and this is 1 volt. This is R. This is R. Now we want to know the feedback quantity, right? Therefore now tell me, if you solve, what you will get? Vf minus 1 divided by R plus Vf minus of minus 15 divided by R is equal to 0. Therefore now tell me, RR will be cancelled. 2 Vf, right? And minus 1 plus 15 minus 14 is equal to 0. Then Vf is equal to what? 7 volt. Your Vf is equal to 7 volt. Am I correct? Not correct. That's why, to not have any silly mistake, it's better. Therefore Vf, 2Vf minus 1 plus 15 is equal to 0. Therefore 2Vf is equal to minus 14. Then Vf is equal to minus 7 volt, right? Therefore what is Vf? Minus 7. Tell me which is more, 0 or minus 7? Here this is 0 and an 8 plus 15. Here 0 or minus 7? 0 is more, output is minus 15. Therefore remember, if output is stuck at 15, let us say it is at 15. If output is at minus 15, it is stuck at minus 15. This is what is called bistable multivibrator, which I am going to explain later on, or bistable element. When I say bistable element, what do you mean by bistable element? Both the states, let us say this is logic 1, this is logic 0, both the states are stable. Let us say this is the scenario, when V0 is plus 15, then we have to disturb the state of V0, then people apply some trigger at plus. When you apply some trigger at plus, then momentarily you have to pull it down, then your V0 will become plus 15 to minus 15. Once you apply trigger and then pulled the node, then V0 is switching from plus 15 to minus 15, it will stay there only. Because it is also stable. That is also solution. Again, if you want to disturb this solution, or if you want to disturb V0, what to do? Again, apply a trigger here, apply positive trigger. When you apply positive trigger, then plus will be more than 0. Then output will be switching from minus 15 to plus 15. Again, when output is switching from minus 15 to plus 15, it will stay there. Therefore, both the states are stable until unless you apply some external trigger at inverting terminal. At inverting terminal, we will not change the state of your output circuit. It will stay there only. Okay, that is what is called bistable element. Therefore, both the states are stable until unless you apply external trigger. We cannot change the state of the circuit. But if you take astable, there both the states are not stable. Continuously we switch from one state to another switch. That is what your square wave generator, which we will see in the next session. Okay, take this problem. The session is over. We have, I think, 2 more minutes. Then in the next session we will see multivibrators: bistable, monostable and astable. Okay, this is what is bistable element. If you ask me, this is nothing but bistable element. Bistable element or multivibrator. Both the states are stable. If V0 is plus 15, it will stay there only until unless you change the state or apply by applying the trigger. How to apply the trigger? That part I will explain from bistable multivibrator, astable multivibrator or multivibrators concept. Okay, take it. We have 1 more minute. I think you know the procedure. You can pause the video and then you can get it. Okay, thank you.